And I'll start right off with sharing screen here. Clean this up. So let me show you where we're headed here. We're looking for something akin to this. We've got enemies that we can chase around. They run away from us. We can presumably shoot them, and they're shooting us with their particle weapon systems. So, so far, what we've basically put together is this three-state AI that has an idling when it can see the target, it can chasing, and when it gets to the right distance, it can jump, and it converts to jumping. And so our character is controlled among these different states by its ability to see and to jump. And so we can set up kind of the logic of this. If we can see and we can jump, then we jump. Otherwise, we chase. And if we can't see, we idle. We set up the can see function just by casting a vector from our target position to where the AI is, forming a distance of that vector. And if the distance is greater than the see distance, then can see is false, otherwise it's true. We added the idea of a field of view to this by using the vector 3 angle between two vectors, the direction to the target, and the transform forward of my AI. So we're forming this angle between these. And if now our test is both if we're inside the C distance and our angle is less than the sight angle, then we return a true. The can jump is pretty simple. Just form that distance. If we're greater than the jump distance, we have a false, otherwise a true. And we went through the basics of this little script here. In start, we cache a copy of the animator so that I don't have to get component it later, and I start the idle function. And in the update, I do the logic as well as setting the Boolean can see and can jump on the animator that controls the animations. And the little logic about whether we jump, chase, or idle. The controller is fairly simple. We have these three states. The default is the idle, and we have these various transitions among the idle, chase, and jump states based on the can see and can jump parameters. We don't actually use speed and direction in here. I mentioned that the idle state came from the raw mocaps that was trimmed down out of one of the raw animations there. And this is, as I mentioned, the great thing about root motion animations is that I don't have to turn the character. The idle function itself is going to do the turning. The chase state was a blend tree with walk forward, turn left, walk forward, and turn right wide, all cut out of raw mocaps. And the jump state was a little aborted jump where the character waved its hand. And the transitions, as I mentioned, were simple. One thing I need to mention about the transitions, be sure the has exit time is off, because we're controlling these with conditions, and you don't want to have both conditions and exit times. That can cause problems. So the idle function is pretty simple. this state equal idle is just for information on the inspector. It's just an exposed variable in the inspector, so I can see what the character is doing. And while I don't need to, I'm setting speed and direction both to 0. The jump is responsible for keeping my AI pointed at the player. So while we're jumping, we want to keep the AI oriented to face its target. So we form a vector, the face direction. We set the Y component of it to 0. This way, when we do the rotation, we don't get any funny tilting based on a Y component. And I use this quaternion slurp, spherical linear interpolation. And it's one of these progressive ones where each frame here, I move a little closer to the look rotation. That is the rotation that puts the forward vector in the face direction. And I'm doing this progressively with an exposed parameter, my rotation speed time dot delta time. So that's just going to orient my player. Chase is more complicated. We need the current direction. And here the current direction is the animator's root rotation, a quaternion, multiplied by the forward vector, which is 0, 0, 1. So multiplying a vector by a quaternion rotation rotates the vector to that orientation. So current direction is going to be the direction I want my animator to point. And I have, is the direction my animator is currently pointing. Sorry. Wanted direction is, of course, the vector between the target position and the animator's root position. Notice I'm not using transform here. I'm using the animator information because the animator is doing the rotating. And I'm going to normalize this one as well because the current direction, since it's a unit vector forward multiplied by a rotation, it's a unit vector. So both these are unit vectors. So that makes life a little simpler. I'm doing the same thing that I did back when we were with the original AI. I'm forming a dot product that tells me whether I'm facing my target or not. If that dot product is positive, then I'm facing them, in which case the direction I want to face is the Y component of the cross product of those two vectors. And if I'm not facing it, I just do this little trick where I put a 1 or a -1 in, depending on the value of that cross product's Y component. So that just turns as quickly as possible. And here I am setting the direction. This is what's going to determine the steering of my player as that direction, as that blend tree turns my player. So that's this little scene right here. My character is idling. I get far enough away, it can't see. It has a field of view, there it can see me, and it moves until it's at the jump distance, and then it transitions into the jump animation. And at this point, it's not fleeing me, which is what we want to add next. So this fourth state we're going to add is the AI flees if the player gets too close. And so two new public distances. A far distance that's going to be greater than my jump distance, and a close distance that's going to be less than my jump distance. And I'm going to add two new tests, too close and too far, with companion private bools, lowercase too close and lowercase too far, to catch the results. And my state diagram is now a little more complicated. I I have basically the same stuff up here. This is a mistake. It should say can't jump. But I now have transitions out of each of the idling, chasing, and jumping states. If we are too close, in which case we convert to the flee and we run until we are far enough away, at which point I revert to idling. So this is our new state diagram. So in update here, I'm going to have my two new tests, too far and too close. I have new parameters in my controller, too close and too far, that I set here. And then I go into the logic, which is now a little bit more complicated, not really. If I'm too close, I'm just going to flee. Otherwise, I go through the same thinking that I went through where I can see, I can jump. I've added a not too far here as well, and jump and chase and idle. So our logic's a little more complicated, but not terrible. Now, the flee function is virtually identical to chase. All I have to do to make a flee function is change the wanted direction to a negative. So the only difference between chase and flee is that minus sign right there. That's it. Everything else works exactly the same way with the dot product and the cross products and so forth. So that makes life pretty easy. Our new controller looks something like this, and you notice now each of these states have transitions out to flee. Chase has a transition out to flee, and jump has a transition out to flee. This might be one of the cases where you use the any state transition to flee, and then I wouldn't need these three transitions out of idle, chase, and jump. But I chose not to do it because it's not that complicated. And here's the one transition from flee back to idle. Flee, by the way, is also a blend tree like the chase, except here I'm using run left, run, and run right. So my player walks toward me, but it runs away from me. So all pretty straightforward. And so this now looks something like this. I've got my player, and because it's immediately too close, it runs away until it's far enough away. Then it idles until it can see me. Then it chases until it's close enough to jump, and then it jumps. And if I pursue it here, it follows me around. Now, one of the issues here is that if I go behind something, it can still see me. So I can't really hide behind this wall here. Well, I got close enough to it that it tried to run away. But I want to add another feature here, the ability to hide behind something. And I'm going to do this with a function check line of sight that uses a Raycast to see if we have a straight line view to our target. I know a lot of you have used Raycast in the either the laser or the shooting with Raycast examples, but I'll go through what we do here. Basically, we're going to have a source position, which is at the eyes. You remember back here with my little AI, one of the things I added to it was some eyes. And I put the eyes up in the head of my object. And the reason for this is that the center of the character, well, it's way up there. I want the pivot. The pivot of my character is at its feet. And so if I were casting this Raycast from my AI to my player, it would emanate from its feet. And so instead, I've added this object, the eyes, that are that I can place basically where the character sees from, in its face, in its eyes. And so my source position is from those eyes position. I form a vector between the source position and the target, and I do a raycast from that source position in that line of sight vector, and I have the out hit that returns information about what I've hit. Now, if I've hit the target, I return a true. If I haven't hit the target, I return a false. So this little piece is going to do the check line of sight to see if there's something between my object. So I want to add this little bailout to the can see, can jump, and to close functions so that they return false if we don't have a direct line of sight to our player. Again, the raycast has an origin where the ray comes from. It has a direction, the vector 3 direction that the ray is cast. It has the hit info that is returned by the raycast function, and the distance, which by default is infinity, but we can set some limit to how far the raycast goes out. And we'll use that with the sight distance. Raycast returns a true if something was hit. It returns a false if nothing was hit, if it's just empty sky. And this raycast hit info has considerable information about what was hit. It has the point in world space that was hit. It has the distance to that point. It has the collider, rigid body, and transform that the raycast hit. And we're using the transform hit that from this output hit that is returned by raycast. And notice it's if physics raycast. So if raycast doesn't hit anything, it doesn't do anything here, and it just returns a false. So we're using that Boolean return of the raycast here to decide whether to do any logic. We can add a gizmo to show the line that that raycast vector represents. We can put this, this is visible in the scene view and in the game view if the gizmo is on. And this is a draw ray, which takes the source position, that's where the ray starts, and the vector that the ray follows out. And in this case, I've normalized the line of sight vector, and I've multiplied it by my C range. So this is going to draw a little line in the scene view that shows how far my character can see. And so now I have a wall that I can hide behind. So my little player is gonna, or my little AI is gonna run away, and I'm gonna move over here behind the wall, and the player can't see me, even though I'm close enough. If I'm behind the wall, the player can't see me. And it won't run away from me either, because it can't see me. And I think this actually works with the terrain too. If I get them to follow me over here and go down behind one of these bumps, the AI can't see me if I'm hiding behind a hill. Oops, I got to get behind a big enough hill so that it can't see me. So, and it's casting it out of its eyes. And as it turns out, it's actually casting to the foot position of my player here. So that's why we could see its head. I thought that was actually a good feature. So let me stop sharing here and see if there are any questions at this point. Remind you to put your name in chat as long as I'm here. Any questions about this? Okay, back to sharing then. So the idea behind this is that I'm going to replace that jump state with an attack state. I'm not going to change names or anything. I'm going to leave the animation the same, jump animation, but I'm going to add a behavior to the animation. So when I get to this jump state and I start jumping up and down, at this point, I'm going to start doing something that will damage my player, the attack. And I'm going to do this with a behavior that is added to the animation. And I'm going to cast particles out of my player and out of my AI, and those particles are going to damage my player. Now, this was a big fiddle because I wanted the particles to come out of the right hand that the player has raised here, or the AI has raised. I wanted the particles to emanate from this hand as if it were casting a magical spell. And so what I did, where are we here? The behavior. So if I drill down into my player here, down through its body, through its pelvis and its torso and its torso B and its torso C, and I think it's down the right arm, the right shoulder, the joint, and here's the hand, the right hand, and here's where I've put my gun tip. This is where the particles are going to emanate from, this gun tip that is placed in the right hand of my character. Let me get the animator here for this character. The animator is idle, jump, flee, behavior, and it looks basically the same as my idle, chase, jump, flee. And here, just to remind you, flee is a blend tree. So in the jump animation, which is just that jumping to, I've added a behavior. Here's the button for adding a behavior. And this added behavior has an exposed variable for the poofer. It has a host target, children, and we'll see what those are in just a minute. Now, state behaviors are not mono behaviors. All of the scripts that we've written thus far have been mono behaviors. They derive from the base class mono behavior that has the API of Unity in it. State machine behaviors are different, and they do lie on top of mono behavior, but they are their own class of functions. And interestingly, the template that gets loaded when you create a state machine behavior, when you create a behavior with that button on the state, it includes a template of all of the relevant functions that are used by a state machine behavior. They're all commented out, but they're all there with their arguments filled out, and they're ready to fly. Now, these functions include the onState enter. And onState enter is called when a transition starts into that state. So the minute the transition starts, the onState enter is triggered. And it has as arguments some information. It has the animator that is calling this state. It has some state info that we'll see, and it also has the layer index. Remember, the hand wave was on a second layer, so this tells us what layer we're in. We also have on state exit. That's called when the transition out of this state finishes and the state machine is no longer in this state. And it has the same arguments as above. There's also on state update, and update is called each update frame. So it's called between the enter and the exit callbacks. And then there's two more advanced ones, on state move, that is called after an on animator move. This is something that we do to keep track of root motion. And there's on state IK, inverse kinetics, which is far more too advanced for here. So in our state machine behavior, and notice here it's not a mono behavior, it's a state machine behavior. I have that exposed variable for the poofer. I have the host target, this array of children and a child and a private game object that I'm going to instantiate. These could all be private except for the poofer, because that's the prefab that I'm going to instantiate when I enter this behavior. So in on state enter, the first thing I need to do is get the host's transform. So this is animator, comes from this argument, animator.transform. So that's the AI that's doing this state. I access its its AI component that has a target that it is chasing. And so the host target is now the thing that my AI is chasing. And I get components in children, the transforms, in my hosts. I get all the transforms in my AI, and I want to look through all of them until I find the gun tip. So this is an array. This children is an array returned by get components in children, and I'm going to loop through that array and find the one whose name is gun tip. That's this thing down here that I put on the hand of my player. And that's going to be assigned to the child. I'm going to instantiate that poofer at the child's position, so where the hand is, and I'm going to give it an orientation that matches the hand. So it's going to be oriented the same as the hand. That turns out to not be important, but I did it anyway. And I'm going to make it a child of that transform. So the instantiated poofer, its parent is the hand, is the gun tip, the child that I've attached to my hand. And this is important because as I wave my hand around, the poofer is now going to follow it. It's going to stay with the waving hand, which is very cool. So in the so it gets its target, it gets the array of children, it searches that array of children for one named gun tip, it assigns that to child, it instantiates the poofer, and it makes the poofer a child of that gun tip. Now, in the on state update, this is the one that's run every frame while we're in this jump state. I'm going to form a rotation that looks at the host target's position. It's the vector between the host target's position and the gun tip's position. So this is the vector between where my gun tip in the hand is and the player that I'm targeting. And so this rotation is going to, this look rotation is going to form a rotation that points the forward vector in that direction. And I'm just going to assign my my geo transform rotation to be that rotation. So this means that my gun tip is always going to be pointed at the player during the jump state animation. And in on state exit, I'm just going to destroy the poofer. So that's my full state machine behavior that is going to control that poofing as I go. The particle effect shoots a narrow cone of particles in the forward direction, which is what we oriented to point at the player. I'm going to use an emission that's based on movement, so it emits 5 particles per distance moved. So as the AI waves its arm and moves the gun tip around, it's going to be releasing particles as a function of the distance that that hand is moved. I've also added the collisions module to set to world. And I've also set send collision messages on, because this is what I'm going to use to damage the player. When my particles hit the player, I'm going to take away player points. I'm doing this by putting a current health script on the player that has an exposed variable health. It starts off at 1,000. And this little current health, all it does is update the health UI text and slider value. The poofer, the prefab of the poofer has a health counter script on it that uses the on particle collision. So this is the object that has the particle system on it. And so it can respond to these collision messages that have been sent by the particles. And so anytime any of its particles collide with something, it's going to return this function with the game object other, the thing that was hit by the particle. If the other's tag is the player, I'm going to access that player's current health, that little script that has the exposed health variable in it, the exposed health variable here, and I'm going to decrement that health variable if the player has a current health script. I'm going to decrement it. So this is going to take points away from my player. And so as I'm standing here getting pummeled by the AI's particle system, you can see my health bar up in the corner there going down as these particles that the AI is throwing out at me, 5 per distance. So every time it waves its arm up, it makes a bunch of particles that poof out. So that's pretty cool. One other feature that you might use of the on-state update is normalized time. Part of the state info is what percentage of the time the animation is played. So if you want some event to occur halfway through the jump animation, you could say if normalized time equals 0.5, then do something. So you can have events occur at particular times during the animation. So let me again stop sharing and see if there are any questions at this point, because that was some pretty heavy lifting with quite a bit of fiddling to get things to look right, to get the animation to play in the right place and do the different things. Any questions? Okay, back to sharing that. So, now one issue with the AI as it stands here is that there's not a lot of randomness. So if I have a bunch of these AIs, they're all going to kind of follow the same path. Another problem is that the idle animation always is a turn right. It always turns to the right. And animations have a mirror option. And the mirror option is pretty cool. Where are we here? I want to be. Well, I may as well be in this one. I'll put it in the stress test. So the idle function, no, not that one. The idle function has this property set mirror, and you can do it manually, or you can say that you want the mirroring to be set with a parameter, in which case I put a little check mark here, and then I have to include a parameter that's going to set whether to mirror the animation or not. And so if I have a turn left animation that I mirror, it's now going to be a turn right animation, or vice versa. So this is going to allow me to easily decide whether my idle function is going to turn to the left or whether it's going to turn to the right when it's idling. And so in my AI's function, I have an animator set bool that I can do in the start function, and I can set the mirror to be a Boolean random value greater than 0.5. So this is going to make half my AIs turn one way and half of them turn the other way when they're idling. And so now when I have my group of AIs, and they go out, half of them are turning to the right and half of them are turning to the left, and so their idling behavior is not quite as predictable. Some of them are turning one way and some are turning the other, so that's a good thing. Now, another thing we can do is make the target position fuzzier. Right now, it rigorously targets the position that my player is. And so if we have a bunch of them, they're all going to kind of walk exactly towards the same point in space. And we can make that target a bit fuzzier by throwing a random inside a unit circle. So the unit circle is a circle of radius 1. And if I throw a random number in there, it's going to be an X and Y position whose magnitude is less than 1 since it's inside the unit circle. I believe there might be an on unit circle as well that would be normalized. And I'm going to change this periodically. I'm not going to do it every frame because that would make our player kind of jerky in its behavior. But I'll do it every once in a while. And so I'm going to keep track of the time. I have some random time that is an exposed variable that is how often my character is going to throw this little random inside unit circle. And I catch a copy of the current time plus that, and that's going to be when I do this again. I'm going to form this target offset that is my random distance, how big I want to make this fuzziness, times a new vector that takes the X and the Y of my random inside unit circle and forms a three-dimensional vector with 0 in the Y component I normalize this to make this unit vector 1 and then scale it by that random distance. Then in the loop where I calculate the wanted direction, instead of a wanted direction rigorously to the target position, I'm going to test if the time has exceeded that random time that I set back here in the beginning. If it has exceeded that time, then I'm going to throw the unit circle again, form a target offset, and reset the next time that I'm going to do this. And my target position is now target position plus that offset, plus this little vector inside the circle. So this makes the target position kind of fuzzier, and I use that in my wanted direction. So this makes the target that the AI is going to a little bit fuzzier. And so they won't all line up and go to exactly the same place in the world. Another minor problem that I ran into was that when I had a whole bunch of AIs, they couldn't see through each other. And so you'd have a kind of wall of AIs that were standing there jumping, and the ones behind it would be just idling because they couldn't see through the wall of AIs in front of them. And so they got stuck in the idle state and they couldn't see. And again, we use one of the Raycast's ability, which is to cull layers. Just like the camera could cull layers that it would see, the Raycast can cull layers that it will ignore. And for this, we need to be a little bit tricky. So I've added a custom layer to all the AIs, very original layer AI. So all my AIs are in that AI layer. And I've added an exposed variable AI layer of type layer mask. And the layer mask is the mask of things that we can ignore with our cameras, the custom ignore layer. And in this case, we're going to ignore the AI layer. And so when I have this set up, my little dude here has an AI layer. This is the layer that I want it to ignore. And all of the other layers are here selectable, but I'm selecting the AI layer. Now, oops, I want to select the AI layer. Now, with the camera, if I had selected that AI layer, it would mean that the AI layer is the only one that the camera would see. It wouldn't see all the other ones. So if I want it to be like this, I have to do something a little tricky. And the way I'm going to do this is I'm going to reverse the bits of that AI layer. Now the layer mask is a 32-bit number with zeros and ones in each of the bits. And our different layers, 32 of them, correspond to those different bits. So if I have all 00100 zeros in those 32 bits, the only layer that it can see is that one bit that is on. The tilde reverses the bits. So this is going to take the 00100 and turn it into 1110111. And then I add that layer to the culling of the Raycast, and it's going to hit everything but the AI layer that is now a 0 in here. So if you watch this as I play here, I'll do a pause so that it starts. Notice this changed to, can't, where'd the mouse go? Oh, escape. Nuts. It's locked up on me. Can't see the mouse. What do I do here? I think I'm going to have to bail here because I think it's locked and, oh, there. Okay, so I can at least force quit. Sorry about this. This is the danger of the escape key, because the escape key is what controls that. Where's Unity? There's Unity. The escape key is what controls the visibility of the mouse, but it's also used for other things. What I was going to show you there is that it was now mixed and it showed all the different layers except the AI layer. And so that was cull. Let me get that Unity started again here. So, well, that's loading. So I added a gun so that I could fight back. So I have a gun script. It's going to have a public game object, the bullet that I'm going to throw at the thing. It's going to have a speed, a number, a bullet count, text and slider for how much ammo I've got, and this Boolean fire that I'm going to use to fire the gun. In start, I'm going to set the bullet count to the number here, load values into the text and slider, and then I'm starting two coroutines. And remember, since this is not a coroutine, the start coroutine doesn't block, so both recharge and fire gun are going to go off and run on their own, and the start function is going to complete. And so the recharge function has its own while true loop that it's looping around in. And it's just going to wait 1 second every time through here. And it's going to test to see if the bullet count is less than the number of bullets that I want to have. And if it is, it's going to increment the bullet count and it's going to update the number of bullets that I have on my text and slider. That's all it does. It reloads the bullets as the bullet count declines. Every 1 second, it adds a bullet. The fire gun is has its own while true loop, and in this while true loop, it's basically going to wait for the end of the frame. But if we've fired and the bullet count has not gone to 0, I'm going to form my vector forward. I'm going to move that position out a little bit in front of my player. I'm going to instantiate a bullet at that position, and I'm going to get the bullet's rigid body, assign its velocity to be the bullet speed in the forward direction. I'm going to destroy the bullet after 3 seconds. I'm going to decrement the bullet count and update the slider and text values, and then wait 1/10 of a second. So I can only fire bullets every 1/10 of a second. And so now in this scene, I can now fight back with these bullets. And I can fire bullets. They're firing every 1/10 of a second. And I believe the bullets have a little trigger collider on them that if they hit an AI, they destroy it. And now I'm out of bullets. And so now my recharge is giving me one bullet every second. So I'm still able to fire, but my fire rate has gone down to 1 per second instead of a tenth of a second. And there's the recharge, recharging it. And I think I'm pretty much done with this, except for some efficiencies that I'll cover on Wednesday. So I'll stop sharing there and entertain any questions about our attacking AI.
For the particles coming out of the AI's hand, can you remind me how it was determined how many particles were coming out?
There were 5 on the emission module. It had none per time, but it had 5 per distance. So as my AI moved his hand up, it fired 5 particles because it moved at about a meter. So it fired 5 particles when it moved its hand up, and it fired 5 when it moved them down.
That's so cool. Okay.
Yeah, it is.
Thank you.
Yeah, clever.
Appreciate it.
Yeah. Anything else? All right. Well, I'm going to stop recording there.